Magnetron sputtering is currently a standard process to deposit coatings from various materials. The thicknesses range from tenths of nanometers to micrometers. These thin coatings are used in the electronics industry, mechanical engineering and other fields. In our laboratory, we are the only ones in Central Europe who mastered the preparation of multi-layer optical elements for extreme ultraviolet radiation and X-ray optics. These mirrors have been developed and manufactured for the Pauwels Research Center for a number of years. The center owns a terawatt pulsed laser developed at the Max Planck Institute in Garching. We also participated in the origin of the concept of nano-composite coatings, now widely used in the coating of cutting tools and automotive engine components for the automotive industry. Projects this laboratory has worked on in the past few years have dealt with the optimization of layers for photovoltaic cells, investigation of thin-film chemical sensors, and dynamically stressed components of automobile engines. Electron beam welding is an advanced method for joining metal parts. The technology has been used at the Institute since 1964. Nowadays it's being developed by the third generation researchers of the Electron Technology Group. The electron beam welding machine consists of two main sections, electronics and physical section. The physical section consists of the vacuum working chamber with the pumping system, the manipulator and the electron gun as the electron beam source. One part of the electronic section is a high voltage power supply to accelerate the electrons. The welded parts are placed in the working chamber and the inner space is evacuated. The electron beam is focused onto the surface of the welded workpiece and the weld is formed by mutual movement. Welding is usually performed without any additional material. The combination of the deflection system and the computer can be used to display the workpiece in the electron microscope mode, to weld along complex paths, or to create seemingly multiple beams for multi-pool welding. The deflection system is also used for engraving and local heat treatment of the surface layer, or in 3D printing using selective melting. A typical feature of electron beam welding is so-called deep penetration effect. Power density of the electron beam reaches such values that the beam penetrates the material very rapidly. Thanks to this, the weld acquires its typical knife-like shape, even for very deep welds. Vacuum as a protective atmosphere, the depth effect, welding of high-temperature materials and reactive metals, and high productivity predetermine electron beam welding for applications in nuclear and automotive industries, in aeronautics and space exploration. The Institute uses electron beam welding in construction of vacuum and cryogenic systems for research projects. Under the contracted research, the technology is available to 50 cooperating industrial partners as well. The long-term research of the electron beam welding technology resulted in an agreement on development of a welding machine with a foreign partner. The real nanoscience begins at the moment when we can not only observe tiny things, but when we can create them. And when we say tiny, we mean small things that are millions of times smaller than your palm or the mobile phone it holds. One of the devices that can create the nano world is the electron beam writer. The following shots show the process of preparing micro and nano structures, or to put it more precisely, exposure on the electron beam writer. Data for an electron beam writer are prepared where else? In a computer. The electron beam writer is controlled, you guessed it, by a computer. Exposure takes place on thin silicon wafers in an emulsion that is sensitive to beam of electrons, much like the old camera shutter clicking and releasing light on a celluloid film for a short time. The image is formed gradually in small boxes, and it takes a while. Our photograph will be exposed for about 4 hours. For everything to turn out well, there must be nearly constant temperature in the laboratory all this time. We just have to watch our thermal expansions while we create the nano world. The same applies to purity. Dust particles hitting the silicon wafer could spoil the whole job. There should be less than 100 such particles per cubic foot in this laboratory. Time to develop. Not in a darkroom, but in a centrifuge. After exposure, there's only a latent image on the silicon wafer, which must be developed like a photograph to form the physical structure. The tiniest details in such an image may be 1,000,000 times smaller than your palm, down to just 10 nanometers. And this is the giant step into the nano world of mobile phones, electronic and optical microcomputers, into the world of fast optical communications, and so on. The electron microscope is an advanced device which allows observation at 1,000,000 times magnification and seeing details of the size of the atom. If we looked at the moon with a similar magnification, we could easily spot the footsteps of Neil Armstrong, the first human on the moon. The scanning electron microscope observes the sample by feeling it point by point with a thin and focused electron beam, recording the response on every point and assembling the image point by point. We've developed a unique low-energy electron microscopy technology. This allows us to eliminate problems common in high-energy microscopy. For example, non-conductive samples, such as office paper, are charged with high-speed electrons in a standard microscope, making observation impossible. Low-energy electron microscopy is very gentle to sensitive samples, such as carbon nanotubes. Not only does it not harm them, but compared to conventional scanning microscopy, it displays them more clearly with more details. The experimental apparatus designed in the ISI has ultra-low pressure approaching cosmic vacuum on the lunar surface. There must be a vacuum in the microscope because otherwise the image would be weak and blurred. The electrons would not make it to the sample through the air. Atomic clean surfaces, however, require cosmic vacuum. However, low pressure is bad for biological samples. It dries them like an Egyptian mummy. succeeded in improving the so-called environmental microscopy to the extent that biological samples can be observed not only intact, but even alive. A live specimen partially submerged in water may even move in the hostile environment of the microscope. The Department of Magnetic Resonance is equipped with an imaging system boasting a magnetic field 200,000 times stronger than the geomagnetic field. Owing to the extreme magnetic field and the miniature radio frequency coils, it can display mice and rats just like the magnetic resonance imaging systems showing human patients in hospitals. The experimental system is open to development of new measurement methods and their application in practical research. This research takes place in collaboration with other research institutions. Magnetic resonance imaging is used not only to display the anatomy of tissues and organs, but also to monitor their function. The image shows biochemical and cellular changes in affected tissues, supply of blood to organs, blood vessels characteristics, mobility of water molecules inside cells, metabolic changes and brain activity. This is essential for diagnosis and research of mechanisms of neurological, cardiological and oncological diseases. Magnetic resonance imaging is also used in the development of new drugs. A marker bound to a nanoparticle carrier, together with recognition antibodies and a drug, make it possible to monitor targeting toward the diseased tissue. The imaging technology thus contributes to the development of drugs and reduces the need for laboratory animals. This work is expected to lead to be effective drugs with minimal side effects. Besides different MR imaging variants, the Institute of Scientific Instruments deals with MR spectroscopy. This method can be used to monitor changes in the metabolism of living cells. The vapor technique, developed years ago here at the Institute, is now successfully used worldwide to reliably suppress the water signal, which is 50,000 times stronger than the signals of the monitored molecules, and therefore, when not suppressed, impede the evaluation of metabolites. The Institute is working with other European institutions on the development of software using mathematical analysis of spectra to provide reliable assessment of biochemical changes in clinical use, and in this way to contribute to early diagnosis of diseases and to medical research. By measuring heat flow in a vacuum between two separate surfaces, we can determine how these surfaces reflect or absorb thermal radiation in a defined temperature range. The special measuring device developed at the Institute of Scientific Instruments can accurately measure such a heat flow up from minus 260 degrees Celsius, and it also manages to measure the heat flow with a very large range of measured output. The studied materials are cooled in a container with liquid helium, which boils at minus 269 degrees Celsius. The dependence of the amount of reflected heat radiation on the type and quality of surface has long been known and is used, for example, in thermos bottles. The glass surface of the thermos bottles is covered with a thin layer of silver, which reflects thermal radiation very well and allows the double-walled bottle to keep the beverage warm or cold. Operation of special cryogenic equipment such as hospital tomographs would be impossible without the use of appropriate thermal insulation. These insulations are frequently formed of multi-layer plastic films on which a thin layer of a suitable metal, typically aluminium, is deposited. Also, any equipment launched into space must be provided with suitable thermal insulation. Solar radiation, which is very intense and nearly omnipresent in space, would soon destroy any equipment in orbit without thermal insulation. In the Institute of Scientific Instruments, we can measure emissivity and absorptivity of heat radiation of any material that can be formed into a flat disk with a diameter of 40 millimeters. The Institute owns a unique database of emissivity and absorptivity of heat radiation for more than 70 different types of material surfaces. Surface preparation is carefully described, and therefore the database has a major practical importance in designing of thermal insulation of cryogenic devices. Our measurements and results are used, for example, to design thermal insulation for the European Space Agency satellites. In this field, precise knowledge of thermal dependence of emissivity and absorptivity of heat radiation by the surface of a particular material is essential to successful satellite design. Every human body is unique. Signals that can be measured and examined are equally unique. For example, electrical and mechanical activity of the heart, propagation of pressure waves in the bloodstream, or the inscrutable and mysterious brain signals. During a heart contraction, a pressure wave propagates through the arterial system. With our unique device, the bioimpedance MBM monitor, developed in collaboration with the St. Anne University Hospital, we can measure the propagation characteristics of pressure waves throughout the body via electrodes stuck to the skin. Thus, we map the condition and age of the arterial system in the extremities and in the trunk. With the financial support of the European Union, we're finalizing the clinical version of the MBM monitor, suitable for early non-invasive diagnostics and prevention. The new monitor is also equipped with a powerful parallel processing in real time, the pulse wave system. It provides the physician with complete information about the individual speeds of the pressure wave propagation in real time. The screener includes a comfortable offline evaluation of previously measured data. The output is a detailed report describing the condition of the arterial system. So far, we know very little about the functioning of the human brain. For over 10 years, we've had new options at our disposal that provided us with very weak signals directly from individual brain structures, measured through intracerebral electrodes. Current invasive diagnostics use advanced acquisition systems with high dynamics and sampling frequencies. Captured EEG records are very valuable. They demonstrate new properties of propagation of electrical activity in the human brain. "200 measured points, 25,000 samples per second, enormous data flow, we have a chance to see signals spreading and links operating among different brain structures at rest during recurring mental activity, as well as links associated with the disease. It is an exciting work that requires high processing power and perfect methods for analysis and visualization. The result is a unique insight into the mystery of the human mind. When photons from a conventional laser pointer focus on particles that are approximately 100 times thinner than human hair, they can really shake these particles. The microparticles are commonly dispersed in a drop of water. However, we can also manipulate aerosol droplets in the air or solid particles in a vacuum. A huge number of photons pass through the focal point of the laser beam. Each of these photons carries energy and momentum, which is transferred to the particle. Each deflected photon imparts a force that can be described by Newton's laws of motion. We can thus design optical tweezers capable of keeping a particle at a given location just by light. Optical tweezers can be used not only for optical capturing, but also for contact-free gathering of information about micro-objects. We use, for example, Raman spectroscopy, which provides information about the type and number of chemical bonds in the micro-object, the so-called chemical fingerprint. We've created a number of unique experimental setups in the ISI, where we study the effect of light on particles of different types and sizes. We can, for example, create several focal centers that are manipulated separately to create complicated structures from microparticles in a controlled manner. Using vortex beams, for example, we spin microparticles to make the ambient fluid flow. Using laser beams tens of micrometers wide, we can very accurately move a number of particles over the 1,000 times the size of each particle. We were the first in the world to create a tractor beam that was previously known only from science fiction. We use it to move particles upstream against the flow of photons. We can sort dozens of particles according to size by simply irradiating the particles with a laser. Finally, we can create entire microstructures. In the near future, we'll be able to create micro-robots with different functions to be used in medical and biological research. For making the tractor beam a reality, the Department of Optical Micromanipulation Techniques was awarded the 2013 Werner von Siemens Award in the category of the most important result in basic research. Vacuum deposition by electron beam is one of the most widespread methods of preparing thin films of various materials for optical purposes. The thickness ranges from nanometers to micrometers. These thin film systems are used wherever there is a need to modify the spectrum of passing or reflected light. As an example, we could mention mirrors for different wavelengths from the UV through the visible to the infrared, anti-reflective layers reducing the natural reflectivity of glass, different beam splitters, and so on. It is used, for example, in laser surgeries, where it is necessary to protect the eyes of the surgeon. Color filters find application in lighting. Anti-glare layers are used, for example, in glass lenses. Other types of filters are used as aids for teaching physics. The filters manufactured in the laboratory serve for optical components developed at the UPT and for external customers in the Czech Republic and abroad, who use them in their products or for their own needs. We have a wide range of gauges to measure kilometers, meters, millimeters. To make sure that we measure lengths correctly, we calibrate the length measuring instruments regularly. For the most accurate calibration, we use laser light, whose wavelength we know very accurately with an accuracy of many decimal digits. The light allows us to perform length calibration with the resolution down to the size of a single atom. In our institute, we've developed a specialized laser length meter, the so-called nano comparator, which can calibrate even the most accurate sensors used, for example, in automotive industry. For this unique device, we won the second Media Award at the International Engineering Fair in Brno. Laser light is reflected from objects with high surface temperature, for example hot forgings or ship propeller shafts. In our institute, we've developed a precise laser meter with which we're able to measure the shape of such objects with an accuracy of 1/1,000,000th of a meter. The most accurate industrial mechanical length standards used are block gauges. In cooperation with Messing, we've developed a fully automated device for non-contact laser measurement of the length of these gauges. The device operates using a unique combination of laser light and white light. We own an industrial patent for this principle, and in 2012, it won us the gold medal at the International Engineering Fair in Brno. The length unit of 1 meter is derived from the wavelength of laser light, which is determined by the physical phenomenon of absorption in superclean gas. We own a comprehensive technology for filling glass tubes with such gases. Our tubes are used for the construction of national standards in a number of countries. We're pushing the limits of measuring techniques by methods using pulsed lasers. These lasers generate short light pulses lasting only a few femtoseconds. If we shut the eyelid for 1 femtosecond, we would blink a quadrillion times per second. Quadrillion is a million billions. Such laser generates a range of wavelengths that are even more accurate than anything we've mentioned before. Our new method of measuring distances using a femtosecond laser was awarded the Siemens Prize for the Best Innovation of 2012. High-power technologies have become a standard part of industrial production. Owing to the high power, laser beam can be used not only to measure materials, but also to divide or weld them. The High-Power Laser Technology Group concentrates on this technology and its development in the ISI. Nowadays, automated laser welding and cutting centers are indispensable for production, thanks to their accuracy and speed. Therefore, in cooperation with industry, we participate in the innovation of the laser devices, their accuracy and efficiency. Everything starts with basic research of welding process. By monitoring the plasma cloud and its properties, we developed a unique diagnostic system for CO2 lasers at the ISI. It can modify its own welding parameters in real time so that the results meet the required criteria. We've been developing this system for fiber lasers as well. In UPT, we also focus on the technological process proper, from the design of the optical path of the high-power laser through assessment of the effectiveness of the methodology to real tests of the 3D laser welding and 3D cutting for specific user applications. In other areas of our research, we focus on the issue of plasma behavior inside a cavity or a combination of laser beam with other available welding technologies.